Hello everyone and welcome back. As usual, we have 5 minutes before the official class start time, so I'll ask if anybody has any general questions. Don't ask though specific questions about the assignment, because it makes more sense for me to answer those during office hours or to see a TA during office hours. And as well, can someone confirm that they can actually hear me? Good. So, any questions? The question is, can we submit handwritten assignments that are scanned in? Yes. I think the web page says that that's allowed. So as long as your handwriting is reasonably good, so that no TA will struggle to read it, you can scan your assignment and submit it as a single PDF file. You can either do that with a real scanner, or I think there are plenty of phone apps now that pretend to use your phone as a scanner and can even make PDF files. How am I doing today? I'm doing very well, thank you. Am I following the NHL playoffs? No, not at all, I'm afraid. I'm not a hockey fan. Do you mind uploading the TeX file for the sample solution for formatting? Sure, maybe the link is broken to that file. I thought there was a sample there, but maybe it's a broken link. I'll fix that hopefully right after class. Okay. Okay, so since there seems to be no more pressing questions right now, I'll start a minute early, just because there's a little review section on the board here. So remember, we've seen this factorial notation, n factorial. That's just the notation for the product, n times n minus 1 times n minus 2 times n minus 3, and so on, all the way down to 1. And one of the reasons that this thing comes up so often, this n factorial, is that it counts the number of permutations of an n element set. So what are permutations? Those are just all the ways of writing the set down in a specific order. So you write each element once. So you create a sequence of length n whose elements are the elements of the set, and each element appears exactly once in the sequence. So for example, here's a set that contains 3 elements, A, B, and C, and here are the possible permutations of that set. 2 of them start with A, 2 of them start with B, and 2 of them start with C. So there's 6 permutations of that set, and indeed 3 factorial. So it's a 3-element set. So that should be 3 factorial should be the number of permutations, and it is 3 factorial is 3 times 2 times 1, which is 6. So n factorial counts the number of permutations of an n element set. So that's a theorem that's written here. And I think we said this and maybe even proved it, but the proof is easy. In fact, we already know two of them. So one proof, you can just use the product rule. So the procedure for writing out a permutation of an n element set is to pick an element from the set and write it down and remove it from the set so we don't pick it again. Right? So you pick the first element. Well, if it's an n element set, you have n choices for the first element. And then you pick the second element to write down. Well, now you have n minus 1 choices. So there's n minus 1 choices for the second one and n minus 2 for the third. And so on, all the way down to the last element that you write down when the set has only one thing left in it. Then there's only one choice. And so you get that the number of permutations that way is n times n minus 1 times n minus 2, all the way down to 1, which is n factorial. Another way to see it is to observe that a permutation is a function from 1 to n onto the set. How is that? Well, just look. When I write down a permutation, that's a sequence of length n, and so each, for the first thing in that sequence, there's something in the set S. For the second thing in that sequence, there's something in the set S. And for the third thing in the sequence, there's something in the set S. And because it's a permutation, everything in S appears exactly once, it means it's a one-to-one function. And we saw actually a general formula for counting the number of one-to-one functions from a set A onto a set B. And when those two sets have the same size, it actually just works out, that formula is n factorial. It's n factorial divided by 1. Okay, so that's just a sort of review / reminder of what we did. Okay, but today the main topic of the lecture, and these have already, people are needing these desperately for the first assignment, is these binomial coefficients. And I want to distinguish between the definition of these things and the theorem about them, which some textbooks and some people don't necessarily remember the difference or make such a big distinction. But here's the definition. I give you two integers. N is bigger than or equal to 0, and k is bigger than or equal to 0. Then this notation here, we pronounce it as n choose k. So it's an n on top of a k, no line between them, we're not dividing, and put in parentheses. That's just the number of k element subsets of a set of size n. Okay. And we have an example of that here. Here's a set S. It has size 4. Its elements are A, B, C, and D. And if I look at the two element subsets of S, so the pairs of elements that I can pick from S, and remember subsets and sets in general, you don't care about order. So if I look at the two element subsets of S, here they are. There's 1, 2, 3, 4, 5, 6 of them. AB, AC, AD, BC, BD, and CD. And you can check that actually there are no more pairs that I can make from this thing. No more two element subsets of S. And so that means that 4 choose 2 has to be this number. That's the definition of this binomial coefficient, and this number is 6. So that's just the definition. That the binomial coefficient n choose k counts the number of k element subsets from usually a larger set of size n. And here's the formula for n choose k, which is given by this theorem. It says that n choose k is n factorial over n minus k factorial times k factorial. And we'll prove this in a second. Some of this maybe looks a little bit familiar to you. This n factorial over n minus k factorial, we've seen that before. And we saw that as this gives you something like, or these ratios, they show up in these one-to-one functions. When you count one-to-one functions from one set onto to another, and we'll see that they come up in the same way here. All right. So I'm going to prove this, and I want to use a technique which will look really strange at first, but will turn out to be really powerful. It's something that we'll use over and over in this course. It's something that I use a lot in my own research. In the textbook, this technique is called a combinatorial proof, but in a lot of other places, this is called either double counting or counting two ways. I don't like the term double counting because double counting also refers to a mistake that people make when they're trying to do combinatorics, when they're trying to count things. They accidentally count things twice when they were only supposed to count them once. So we'll call this counting two ways. And the general technique for counting two ways is I have two formulas, F1 and F2, and I would like to show that F1 equals F2. So for example, here I have two formulas, or two expressions. On the left I have n choose k, and on the right I have this thing n factorial over k factorial n minus k factorial. So what we do is we define a set A. Okay, so we're going to define some set A, and we're going to show, so we make some argument. We use whatever the rules we have. Often the product rule comes into it. And using that argument, we'll show that the size of A is equal to F1. Okay. And one thing that you may or may not have noticed yet is often there are different arguments you can make to count things like the size of some set. And these arguments look like they give you different answers. So for instance, the product rule is a really common source of this, where when you have a procedure that generates things, it's very often easy just to reorder the steps in the procedure, and then you get a different looking formula. Now, of course, you don't get a truly different formula because when you take the product of things, the order in which you take the product doesn't matter, but you get something that looks different. So you make an argument here, and you prove that the size of A is equal to F1. Now you make another argument, and you prove that the size of A is equal to F2. And if both of your arguments are correct, so that means the size of A is equal to F1, and the size of A is equal to F2, well, that means that F1 is equal to F2, right? The equality is transitive. And so if both of these things are true, size of A equals F1, size of A equals F2, well, it better be the case that F1 equals F2. Okay. And that's what we're going to do here. And the trick, of course, again, it's another example of an extremely simple idea that all of the power of it comes in the clever arguments that you make and the clever choices of this set A. So let's do that. So here we're going to take the set A, so let's be really clear. Let's say let S be a set of size n, and let A be the ordered k-element subsets of S. And the key word here is ordered. So subsets in general are not ordered. So when I say that I'm talking about an ordered set or an ordered subset, what I'm talking about is a sequence that includes each element exactly once. Okay? So, for example, in this example, we had 6 subsets of the set S here. These were AB, AC, AD, BC, BD, CD. But if I look at the ordered subsets of S, then I get 12 of them. And the reason I get 12 of them is that I will get AB, but I also get BA. And I get AC, but I also get CA. I get AD, but I also get DA. I get BC, but I also get CB. I get BD, but I also get DB. And I get CD, but I also get DC. So the number of subsets of S of size 2, the 2-element subsets, is 6, but the number of ordered 2-element subsets is 12. So we're going to count, we're going to figure out the size of A here. Okay. So we're going to do that in 2 different ways. So here's one way to count the size of A. We'll use the product rule with 2 steps. Step 1 is choose a k-element subset of S. And step 2 is choose an order. For this subset. Okay. So, choosing a k-element subset of S, S is an n-element set, so we actually have a definition that tells us that the number of ways to do that is n choose k. So for instance, in this this example, I choose one of these subsets. Maybe I choose AC. So it's the subset that contains these 2 elements, A and C. Step 2 is to choose an order for this subset. So in this example, there are 2 possible orders for AC. I can write AC or CA, so there's 2 possible orders. But in general, so an order, that's just a permutation of the subset that I have. So here there were 2 ways to do it, but in general, if there's k elements, there's going to be k factorial ways to do it. And once I follow this procedure, then I will have generated an ordered k-element subset of S. And it's easy to check that for any k-element subset of S, ordered k-element subset of S, there's a way to generate it this way. And if I execute this 2 different ways, if I change either of these steps, then I'll get a different ordered subset, either because I get a different subset, the elements are not the same, or because the order is different. The elements are the same and the order is different. Okay. So that tells me that the size of A is equal to the product of these 2 things. It's n choose k times k factorial. So let's count the size of A a different way now. Also using the product rule. And we'll use k-step procedure. At each step, we choose the ith element in the ordered set. So rather than do these two steps here, I'm going to remember, I'm supposed to write out a k-element sequence consisting of distinct elements of S. So in the first step, I will choose the first element to write down, and in the next step, I'll choose the second element, and the step after that, I'll choose the third element, and so on. So how does that work? Well, and the example here is, if I wanted to generate a two-element sequence consisting of distinct elements of S, so an ordered subset, then I choose the first element. So S has 4 things in it. So I choose maybe the first element, D. That's when I equals 1. And now I equals 2. I choose the second element. And I'm not allowed to choose D again. I can choose A, B, or C. So maybe I choose B. And that generates that particular subset. Okay. So how many ways are there to execute this this procedure? Well, there's k steps. And in the first step, I can take anything I want from S. In the second step, I can take anything except for the first thing that I picked. So there's n minus 1 things. In the third step, I can take anything except the first 2 things that I picked. So there's n minus 2 options. And in the last step, in step k, I have already picked k minus 1 things, and I'm not allowed to pick those anymore. So that's n minus k minus 1. Okay. And this we have seen before, actually. This is exactly the same thing that was happening when we were defining one-to-one functions, and it's happening for exactly the same reason, because the procedure is the same. So again, we have a complicated formula, or not a complicated formula, but something that starts out to look like a factorial, but doesn't quite finish. So let's complete it. So here we get n minus k would be the next thing, and then n minus k minus 1 all the way down to 1. We put that on the top and bottom. And so what we get is, on top we have n factorial, and on the bottom we have n minus k factorial. So the size of A, the number of ordered subsets, k-element ordered subsets of an n-element set, is equal to this formula. So we defined the set A, we counted it, we got this formula. We counted it again, we got this formula. So these two things must be equal. Now, that wasn't exactly what we were trying to prove. We were trying to prove this, but if we take this thing and multiply both sides by, or divide both sides by k factorial, then we'll put a 1 over k factorial here. A we don't care about anymore, and we get a k factorial down here. This and this cancel out. We don't care what's in the middle here. But over on the right-hand side, we have n factorial, n minus k factorial, and on the left-hand side, we only have n choose k, which is exactly what we were trying to prove. N choose k is equal to n factorial over k factorial, n minus k factorial. Do you have to prove the combination formula if you use it on assignments or tests? No. So this is, in general, when there's a theorem that we prove in class, when you use it on, when you're allowed to use it on an assignment or a test, you just cite it and say, you know, this, you know, something is equal to something by theorem whatever in the textbook or the theorem that we proved in class. Okay? So you won't have to prove it, but of course it's important to follow along and understand these proofs because you will have to prove things that are like this or more complicated. And you're seeing that already on the first assignment. Proofs that we did in the first class, you're already having to understand them well enough to generalize them to stronger statements. Okay. Good. So let's just remember the general technique here. This double counting or counting two ways. Define a set A, show that it's equal to something, show that it's equal to something that looks different, and then conclude that those two things which look different must actually be equal. We'll see a few examples of that today. All right. So here's an easy example. How many five-card hands of a 52-card deck are there? Okay. So the standard deck of playing cards has 52 different cards in it. So that is a set. It has 50 of size 52. So all the elements in the set are distinct. So it really is a set, and it has size 52. And you want to know how many five-card hands are there. So a hand is, you know, someone takes this this deck and chooses 5 cards from it and gives them to you. How many different ways are there for that? You know, what's the number of different five-card hands? Well, just by definition, the answer is 52, choose 5. Okay. And by this formula, that's 52 times 51 times 50 times 49 times 48 divided by 5 times 4 times 3 times 2 times 1. So that's the number of 5-card hands of a deck of cards. And just so you have a feel for it, that is about 2,598,960. So this kind of stuff is useful to know if you're a poker player, where in many cases a poker hand is 5 cards. You know, how many different possible hands are there? There's this many. And later when we start doing probability in this course, we'll see that, yeah, this number is really important because when we're computing probabilities, this is the denominator in some probability. These are all the possible hands I could get, and if I'm interested in what's the probability that I get a good hand, where good has some very specific definition, well, it's the number of good hands divided by the number of these hands. So this is really important if you're a poker player. And it's worth noting that this is a pretty big number, right? 2.5 million. So it's not reasonable as a human player to somehow have a rule where you remember exactly what you should do for any hand that you get. That would be 2.5 million things you would have to remember. And it's really not useful because it's worse than that when you're playing poker. There's not just the 2.5 million hands that you could get, but there's all the other possibilities in the game for what other people are showing and what you should do in those cases. So there's no way for you as a human to have just a lookup table that tells you what to do. Unlike some other simpler games like blackjack, where you can actually have such a table. Okay, so that's an easy example, and here's another easy example. How many bit strings, remember these are binary strings of length n, have exactly k ones? So a couple of questions, old questions. What was the name for 2 in that previous proof, the II? That was also an application of the product rule. So both of those were applications of the product rule. We just used different procedures, and we got what looked like different answers. Yeah. Okay, so how many bit strings of length n have exactly k ones? Well, the notation that I've used maybe is giving away the answer, but there's an easy way to see it. To prove this, let's use the product rule. So I want to write down a bit string of length n that has k ones in it. First thing you do is choose the locations of the k ones. And the second thing you do is and write them down. And the second thing you do is write zeros everywhere else. Right, if I want to make a 6-character string, bit string with exactly 3 ones, well, the first thing I can do is choose where the ones go. Maybe I would like to put a 1 here, a 1 here, a 1 here. That gives me exactly 3 ones. And everywhere else I put zeros. And that gives me a bit string of length 6 with exactly 3 ones. And you can check that this is a valid application of the product rule for any bit string with exactly 3 ones. There's a way to execute this so I get it. When I execute this 2 different ways, then I get 2 different bit strings. So what's the number of ways of doing the first step? Well, this is n choose k, right? I have k locations, or I have n locations where I can put the ones. I choose k of them, k different ones. So that's just a k element subset of the n possible locations. So that's n choose k. And how many ways are there to write zeros everywhere else? Well, there's only one way to do that. So the answer is n choose k, which we know has this sort of closed form formula. Okay. All right. So any quick questions before we continue? Good. So now we're going to see something kind of cool. And this is what the textbook calls Newton's binomial theorem. Okay. And it says for any numbers x and y and any integer then x plus y to the n is equal to the sum k equals 0 to n of n choose k x to the n minus k y to the k. So this is Newton's binomial theorem. It looks kind of scary the first time you see it. Let's just check it out. So it talks about these binomials where you have the sum of two things raised to some integer power. So for example, you've seen these before. One of the things you do in sort of first times you're introduced to algebra is maybe looking at formulas like this, x plus y squared, and you remember there's this rule, at least when I studied it, it was called the FOIL rule, that when you want to write out all the terms of this, you want to expand it, you get an x squared, you get a xy, you get another xy, and you get a y squared, and that's x squared plus 2xy plus y squared. And this is actually a special case of Newton's binomial formula, right? So this binomial formula tells us what these coefficients are. The coefficients are 1, 2, and 1. So let's check that. This here, it says the coefficient should be, so n is 2 in this case. So that should be 2 choose 0 x squared. Here, so we take k equals 1, we get x to the 2 minus 1 is x, y to the 1 is y, and the coefficient should be 2 choose 1. And then finally, when k equals 2, we get x to the 2 minus 2, that's x to the 0. We get y to the 2. And the coefficient should be 2 choose 2. And indeed, 2 choose 0. How many 0-element subsets are there in a set of size 2? There's exactly one of them. It's the empty set. So indeed, this is equal to 1. So the coefficient on x squared is 1. 2 choose 1. How many different ways are there to choose a set of size 1 from a set of size 2? Well, there's 2 ways to do that. If the set is A and B, well, it's AB. I mean, it's A or it's B, so that's 2. And how many ways are there to choose a subset of size 2 from a set of size 2? There's only one way to do it. You have to take the whole set. So that gives you 1. So Newton's binomial theorem tells you how to do that, not just for the case when n equals 2, but it gives you the formula for any value of n. And that's good because in general, if I look at x plus y to the n, this rule, FOIL, first, outside, inside, last, which is the one we use when n equals 2, it gets kind of long. In particular, when you have when you have a power 3 here, right, that gives you something like, x plus y cubed, that's x plus y times x plus y times x plus y. That gives you 8 terms when you expand it the long way. So you don't just get 4 like you get with this rule, you get 8 when n equals 3. And when n equals 4, you get 16. And when n equals 20, you get over 1 million of these things. And so it's helpful that Newton has this nice clean formula for us. And where does it come from? Well, it comes, how does this formula arise? Or what does the proof look like? Well, it really comes from exactly what we've just been doing. When I take x plus y to the n, and I write it out longhand, that's x plus y times x plus y times x plus y, and so on, n times. If I want to write out longhand what all of the terms are, well, what I do is I walk through this sequence, and I pick for each of these factors, I choose to either multiply by x or multiply by y. So for example, if each time through I choose to multiply by x, then I'll get x to the n. If I choose one of the times when I go through, so for example, maybe I take x, 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 and then the last one I take y, well then I would get x to the n minus 1 times y. Now, how many ways, so the number of ways that I can get x to the n here, there's only one way. I have to choose x every single time. But how many ways are there for me to get x to the n minus 1 times y? Well, I can choose x the first n minus 1 times, and then choose y. Or I can choose x the first n minus 2 times, choose y once, and then choose x again. In particular, each time I choose y exactly once, I will get this term again. So really, the number of ways to get this term is n choose 1. So I pick the place where I'm going to choose y, everywhere else I choose x. So then I get n choose 1. And similarly, for x to the n minus 2 y squared, I choose two places where I'm going to pick y, and everywhere else I pick x, and that gives me this n choose 2. And so on, right up until the end, when it basically says to get y to the n, the only way to get it is I have to choose y every single time. There's only one way to do that. Okay, so someone asks, you understand how to find the cardinality of the total number of subsets of size k, that's n choose k, and we have a formula for it. How do you find the cardinality of the total number of possible, of all subsets, forgetting about the size? Well, we've seen that already. If you want to know what is the total number of subsets of a set of size n, it's 2 to the n. That's that we did already when we looked at the bijection between these things, subsets of an n-element set, and bit strings. So there were 2 to the n possible bit strings of length n, and there's a bijection between those and subsets of an n-element set. All right. So that's Newton's binomial theorem. This is the sort of hand-wavy version of the proof, but I think everything's sort of easy to check here. It's just, I mean, you try and do this multiplication longhand, figuring out what each of the 2 to the n terms is, and you realize that that x to the n minus 1 choose y shows up n choose 1 times, and in general, x to the n minus k times y to the k shows up n choose k times. So what's Newton's binomial theorem good for? Well, it's great for picking out coefficients in one of these big things. It's great for evaluating one of these things quickly, because this thing only has n plus 1 terms, whereas if you do it longhand, you get 2 to the n terms. So that's really slow to do longhand. What are some examples of it? I'll show you 2 examples. One is kind of a boring one. What is the coefficient of x to the 12, y to the 13 in x 2x minus 5y to the 25. Okay. And so the main point of this example is to show you that the application of Newton's binomial theorem really is works whenever you have a sum of 2 things, even if one or both of them are negative, raised to an integer power. So here I have a sum of 2 things, 2x minus 5y. Okay, so if I write this out, this is 2x plus minus 5y to the 25. So it's better to think of it that way. And the thing asks, what's the coefficient of x to the 12, y to the 13? So that means we want y to the 13. So we're going to be looking for this thing, there's going to be 25 choose 13. That's going to show up in there. But here, what we have as the first variable is 2x, not x. So when we take that thing, so we're going to get a 2x to the 12. And the second variable is a minus 5y. We get that thing to the 13. And the question wants to know what's the coefficient of x to the 12, y to the 13. So we need to get rid of, we need to separate these things. So that is x to the 12, y to the 13. The 25 choose 13 is there, but we also have a 2 to the 12, and we also have a minus 5 to the 13. So minus 5 to the 13 is a negative number. So a negative number to an odd power is a negative number. So we get a minus sign in front, and we get a 5 to the 13. So that's the answer to this question. Okay. The question, that particular question itself is not so important, but it shows you, it's an illustration of how you use Newton's binomial formula even when the thing that you have looks a little more complicated. It has a negative part. There's x is multiplied by something and y is multiplied by something, but you can still sort it out. So the answer to this question is the coefficient is minus 25 choose 13, 2 to the 12, 5 to the 13. Okay, good. Here's another cool one. Here's a theorem. The sum k equals 0 to n of n choose k is equal to 2 to the n. So I claim that this is true. And here's a short proof, but it's not the most illustrative. Let's look at 1 plus 1 to the n. That looks like Newton's binomial formula, right? So Newton's binomial formula says, so that's Newton's binomial formula when x equals 1 and y equals 1. So the formula says that that's equal to the sum k equals 0 to n of n choose k times 1 to the n minus k times 1 to the k. But of course, multiplying by powers of 1 doesn't change anything. So that's just the sum k equals 0 to n of n choose k. But wait a minute. This is even more trivial than that, because 1 plus 1, that's just equal to 2. So if we take a step back, we have a string of equations here. On one side we have 2 to the n is equal to 1 plus 1 to the n. By Newton's binomial theorem, it's equal to this sum, which the 1's disappear because they don't do anything. It's just equal to this thing. And so there's the 2 to the n over here, and here's the sum over there. That shows that these two things are equal. Okay. So there's a very short proof of this. There's a nicer way to think about this, and it comes back to a question that one of you asked. 2 to the n, this is the number of subsets of an n-element set. So that's another something we saw. The number of subsets of an n-element set is 2 to the n. Now, n choose 0 is the number of subsets of an n-element set of size 0. N choose 1 is the number of subsets of an n-element set of size that have size 1. N choose 2 is the number that have size 2, and so on. So actually, over here on the left, this is number of k-element subsets of an n-element set. So actually, there was another way to get this formula using more combinatorial reasoning. In fact, what we would be specifically using is the sum rule, because if I want to know how many subsets there are of an n-element set, I can count the number of subsets of size 0, plus the number of subsets of size 1, plus the number of subsets of size 2, and so on, all the way up to the number of subsets of size n. So that's what this formula is. It's another combinatorial proof of this formula using the sum rule. But it falls out somehow instantly from Newton's binomial theorem. Yes, when you take x and y equals to 1, that's what happens. Okay. So now we're going to do a couple of more examples of combinatorial proofs to prove a few classic results about these binomial coefficients. So here's the theorem. N choose k is equal to n choose n minus k. Okay. So here's the proof. We let S be a set of size n. And we let A be the set of k-element subsets. Okay. This is a really easy combinatorial proof. So, by definition, so A is supposed to have every k-element subset of S. So by definition, the size of A is equal to n choose k. That's just the definition of n choose k. It's the number of k-element subsets of a set S. So that's one way to get the size of A. Here's the second way to get the size of A. Let's use the product rule. Choose n minus k elements in S and remove them. And then return the remaining remaining k elements. Right, so I have some set S. I want to pick a k-element subset, so I can either do it directly by picking k elements, and I get that subset. So for instance, for k equals 2, I might pick, or 3, might pick these 3 elements. On the other hand, there's a totally other different view of how to do this. Rather than pick the elements directly, I pick n minus k elements and delete them. And what I'm left with are k elements, the ones that I'll consider to be picked. So the number of ways of choosing n minus k elements from S, by definition, that's n choose n minus k. So that's the size of this set A as well. Right. So we conclude that this set A of k element subsets of S, it has size n choose k directly by definition. It also has size n choose n minus k by this alternative way of generating elements from the set. And so so n choose k must be equal to n choose n minus k. So that's an easy one to keep track of using this intuition that right, I can either pick the elements that I want to keep, or I can pick the elements that I want to throw away. In either case, I can generate exactly the k-element subsets of S. In one case, I'm picking this many elements. In the other case, I'm picking this many elements. Okay. Good. So let's put some of those aside. Useful facts to remember: n choose k is equal to n choose n minus k. Here's another nice binomial identity that says n plus 1 choose k is equal to n choose k plus n choose k minus 1. And this thing is called Pascal's identity. Okay. And if you've ever seen that picture of Pascal's triangle, you maybe have an idea where this name comes from. Pascal's identity, Pascal's triangle, they're based on the same thing. They're based on this formula here. Okay. So what's the interpretation of this formula? Interpretation is, if I want to know, pick k elements from a set of size n plus 1, well, this is the number of ways to do it. And here's the proof. It's again by double counting. So let S be an n element set. let let S be a n plus 1 element set, and let A be the set of k element subsets of S. So by definition, the number of k element subsets of an n element set, of an n plus 1 element set, is n plus 1 choose k. Right, so that's the easy part of this counting, and very often these combinatorial proofs have an easy part and a more interesting part. So there's one side of the formula. Now we want this other side. So here's what we do. We take our set S. We pick one special element in S. Okay? So that means there's n other elements, and then there's this one element here. Okay. So how do we get subsets of S? Well, we split into two parts. Let's call this thing X. So let A1 be the sets in A that include X, and let A2 be the sets in A that don't include X. So we just arbitrarily pick some special element out of these n plus 1 elements, and we say it's special, and then there's the rest of the elements that are not special. And now when we consider a subset, a k-element subset, well, it either includes X or it doesn't. If it includes X, then it's in this set A1, and if it doesn't include X, then it's in this set A2. Now A1 and A2, those are definitely disjoint because every set either includes X or it doesn't. So that means A, the set of all k-element subsets, the size of it must be the size of A1 plus the size of A2. Right? That's the sum rule. And we're allowed to use the sum rule here because A1 and A2 are disjoint. The sets in A1 contain X, the sets in A2 do not contain X. All right. Now, for A1, these are sets that contain X. So a set in A1 contains X, and it contains k minus 1 other things that are not equal to X. They come from this set here. Well, that means to get a set in A1, I pick X, and then I choose k minus 1 other things from this set of size n. So the size of A1 must be n choose k minus 1. Now to get something from A2, it's a similar procedure. To get something from A2, I don't pick X. Instead, I choose all k elements from these things, being non-special. That means the size of A2 is n choose k. So the size of A is n choose k minus 1 plus n choose k. So n plus 1 choose k is n choose k plus n choose k minus 1. Okay. All right. So that's a nice one, and it's the basis of Pascal's triangle, right? Pascal's triangle is a compact way of writing out the binomial coefficients. It's this thing that looks like this. Where are these numbers coming from? Well, this 2 is the sum of these two 1s. This 3 is the sum of this 1 and this 2. This 3 is the sum of this 1 and this 2. And so on. So here we get 1, 5, 10, 10, 5, 1. The sum of these things. And if we think about this, the n plus 1th row in Pascal's triangle, that's this thing. Each entry in that row is the sum of two entries in the previous row. Okay. So row n plus 1 is the sum of two entries in row n. That's where this comes from. Okay. All right. And now we will do a beautiful theorem, which, when you see the statement of it, looks intimidating, but I think we've worked our way up to it now so that it won't be such a shocker. And its proof won't be such a big shocker. So the thing to remember about the proving Pascal's identity is we just took our n plus 1 element set and we treated one of those elements as special, and we distinguished on our two subsets on whether they contain that element or not. And Vandermonde, so this theorem here is called Vandermonde's identity. If you do linear algebra, you may have seen Vandermonde matrices, which have nice determinants. This is something else. And it says that m plus n choose r is equal to the sum k is equal to 0 of r m choose k times n choose r minus k. Okay. All right. So scary looking thing. It says we have a big set of size m plus n. We want to choose our things from that set. And it says, well, here's a formula for that. You sum up k equals 0 to r, m choose k times n choose r minus k. I mean, this looks daunting, but it's not actually. Here's the trick. So this thing is talking about a set S of size m plus n. That's what this thing is talking about, right? The number of r element subsets of a set of size m plus n. So let's just take S and split it into two sets. One of them has size m, and the other one has size n. Okay. Now we let A be the set of R element subsets. That's this thing in the middle that we're going to count in two different ways. Already we get a cheap side. S has size m plus n. A is an R element subset of S. How many of the elements of A are all the R element subsets of S? How many of those are there? There's m plus n. Choose R. That's just the definition of the binomial coefficient. And now we're going to do the same strategy we used for Pascal's identity, but just a little bit more detailed. We're going to say for each k in 0 up to R, we're going to let AK be all of the subsets in A that include exactly K elements from these guys here. So let's give them a name. Let's say these special M elements, let's call them S1. And these special N elements, let's call those S2. Okay. So AK is all the subsets in A that include exactly K elements from S1. Which means they contain exactly R minus K elements from S2. From S2. Now, right, so if you give me any set of size R, so it's a set in A, so it's of size R, it contains, in this case, if R is 4, this one contains 3 elements from S1 and 1 element from S2, so it would be in the set A3. Right, so we just partition A up into sets depending on how many elements of these M elements that they contain. Similar to what we did in the previous example, except there was only one special element and n other non-special elements. Now, well, there's a bunch of special elements and a bunch of non-special elements, so it's not just 0 or 1 possibilities. All right, so now we're just about done, because if we can use the sum rule, right? So A is equal to the union of A1 and A2 and A3 and A4. In fact, A0, A1, A2, A3, A4, all the way up to AR. Right, because any R element subset contains 0 elements of S1 or 1 element or 2 or 3 or 4 all the way up to R. So that means that this is the size of A0 plus the size of A1 plus the size of A2 plus the size of AR. Easier to write that more concisely. K equals 0 to R of the size of AK. And what is the size of one of these AKs? Well, to get the size of AK, we can use the product rule. Where we choose k elements from S1 and then we choose r minus k elements from S2. If I want something, a set of size r that has k elements in S1, then I choose those k elements in S1, and then I choose the r minus k elements in S2 that fill it in to make it of size r. So there's the product rule that tells us that we can use the procedure that we can use to determine the size of AK. And well, the number of ways of doing this first step is the size of S1, which is m, choose k. And the number of ways to do the second step is the size of S2, which is n, choose r minus k. So that sum, this sum here, we can replace these things with, here we get m choose k, n choose r minus k. So the size of A is equal to the sum k equals 0 to r, m choose k, n choose r minus k. Let's write that back up here. And look at that. On the left-hand side, we have m plus n choose r. On the right-hand side, we have the sum k equals 0 through r, m choose k, n choose r minus k. That's Vandermonde's identity. So this really bizarro-looking identity that if we were just working with the formulas, if we were just working with these things, it would be very difficult. I mean, it's possible, but it would be very difficult to prove using, the normal rules of algebra that this thing is equal to this sum. Right? This thing is quite simple. It just looks like this, right? Except you replace m with m plus n, and you replace k with r. That's what this thing on the left-hand side looks like. This thing on the right-hand side is a huge sum. It's a sum with r plus 1 terms. It would be really not obvious how to prove that that is equal to that. But as soon as we realize that these things are just two ways of counting this same thing, what we're counting is the number of subsets of size r of a set of size m plus n. Just two different ways of counting it, then it all somehow becomes easy. And the trick is just to say, well, a set of size m plus n, we can partition it into a red set of size m and a blue set of size n, and then count how many red things, count separately the sets that have no red things, the ones that have one red thing, two red thing, and so on. All right, so that's it for today. I can answer questions for 5 minutes if anybody has any. What's at the top of the sum? R, yes, R. Someone answered that already. Any additional questions? Anything you would like me to clarify? So don't feel intimidated. Just these things, first time you see them, there's a lot in this lecture in particular. Was kind of a heavy one. We did a lot of things. But what I wanted to somehow illustrate is that we didn't do a lot of complicated calculations. Because we're all somehow reasoning about the sizes of sets. Even though we get a complicated looking formula, there wasn't really much going on where we were canceling things or using any really strange identities. We're just counting the size of a set. And we did it the obvious way, just by definition, and then a way that's a little more elaborate and gives us this weird formula on the right here, and shows us that this simple formula is actually equal to this weird looking formula. Okay, so can we do these proofs using the formula directly? I mean, just using the formulas for n choose k and m choose for these things, I wouldn't want to try it. It would be long. Probably we could eventually do it, but we wouldn't really learn anything from it. The real knowledge here comes from understanding that this is true because these two things count the size of the one particular set. On the assignment, when it says to prove or disprove something, are we allowed to use only words to explain? Yes, provided that your words actually explain this thing. So we'll find in this course there's not a ton of calculation. I mean, there's some simple things that we did, you know, that sort of the common thing we do is we take a partial factorial and turn it into a ratio of two factorials. That's not a difficult thing. So in general, there's not going to be tons of formulas that you have to deal with. So many times, words are the best thing. The first approach to counting A always seems obvious, but the second seems to come out of nowhere. Yes. So, I mean, the nice thing about this is if you don't care, if you just want to generate these kinds of weird results, and we'll see some more examples. And the product rule is great for this. If you want to just generate weird identities, then yes, you can take something that you know easily how to count. For instance, here it's easy because that's just the definition of this binomial coefficient. But then you also know how to use the product rule and the sum rule now. Those are the two main ones that give these weird identities. So, you know, if the set is interesting, you can probably also count it with the product rule and the sum rule, and whatever answer you get will probably look significantly different than the obvious way. And when that happens, then you get one of these identities. Now, when someone says, oh, here's an identity, I think it's true, you find the set that goes in the middle, that takes some care, but this is yeah, I mean, that takes some care, and sometimes it takes some brilliant insight. But now you know one sort of approach to doing this, which is to take your set over here on the left and treat it as having two different kinds of elements, the ones in S1 and the ones in S2. And in fact, if you want to fool around with this, see what happens when you have a set of size L plus M plus N, choose R, and you split that set up into three different color classes. Then you'll get another weird formula here. In fact, you'll get a formula with a double sum, really complicated looking thing. That's a generalization of Vandermonde's identity. Yeah, so for the second method, you use intuition, or Maybe you just do the counting and you accidentally discover an interesting identity, and then you say, okay, that's now my identity. All right. So thanks everybody for showing up and listening.